So welcome to my talk at CPP or C++ Online for this year's initial conference, and I'm excited to be able to speak to you, even though I cannot see actually your reactions. So whenever you have a question during my talk, please uh, ask the question within Discord. I have the vulnerable CPP channel open and try to keep an eye on that. And Tim in the backstage will also try to help me paying attention. I might even ask you some questions, so feel free to push your answers there as well. Now, who am I? I'm Peter Sommerlad. I think many of you, if you're caring about C++ and attending conferences on C++, might have heard from me. I'm a regular contributor to the ISO C++ standard. I am giving trainings on C++, so if there's any need, just give me a call. And I'm quite happily, uh, let's say, giving out thoughts on social media, on Mastodon, for example. You can find a lot of the stuff that I'm doing and providing either for the public domain or at least for my teachings on my GitHub account, like the slides as well. Now, what is vulnerable and why do we have to care about C++? Well, vulnerable, if you look at the dictionary, means you're either in danger or exposed to something that is either dangerous or unpleasant or not really nice. And if you're invulnerable, well, you're a superhero. So you might be well protected. And if you look at code, which is vulnerable, it usually means that there exists a danger at runtime. However, we program at compile time in C++ or before compile time, so our programs might consist stuff that we might need to prevent or at least take care about what makes our programs vulnerable. So they might either be insecure or in safety critical domains, they might cause unsafe systems, which is also quite dangerous. So what makes code vulnerable? One big thing that is either on one hand a benefit inherited from C, but also a curse. It's what is called undefined behavior. C and C++ share that property that some of the behavior of the language is deliberately either defined as being undefined, giving compilers and library implementers leeway. Uh, and it might accidentally be undefined because there's a hole in the definition. And compilers became much more clever in the past decade or so, or maybe 1.5 decades, to actually exploit undefined behavior as an opportunity for optimization. Well, because you as a programmer are not supposed to cause code to have undefined behavior, which is kind of the compiler believes you're a superhero programmer and make everything right, which is naturally not always, unfortunately, the case. Even superheroes might have problems getting things right every time they're trying to do that. Just think of Kryptonite being in the vicinity of Superman. Now, there are two more cases beyond undefined behavior that can make programs problematic. One is implementation defined behavior, such as how many bits or what is the range of an int variable or int value. You have no, it depends on the machine. I've lived in times when an int was 16-bit and the largest integer number was 32,767, if I remember correctly. And now most we have, or many, I lived into a long time where ints were mostly 32 bits long, and we might have machine settings or compiler settings where we can actually make an int 64 bits long today on today's 64-bit processors. Implementation defined behavior is good in the sense that in theory, the ISO standard requires compiler vendors to tell you what their implementation decision has been. So it actually must be documented. With open source compilers, sometimes they are on the standpoint, yeah, please look at the source code of our compiler. there the definite truth is documented what our implementation defined behaviors are, which is kind of technically correct, but not always very nice. And there is even a third category where the ISO C++ standard deliberately doesn't define things, but makes it clear it's not undefined. So it's where the compiler vendors or library vendors get leeway in implementation techniques. That's when the standard says the details on how to implement that is unspecified, but the standard then at least gives a guideline what the desired results are, but wouldn't tell exactly what mechanism to use on a machine language level to implement the C++ abstract machine. Now, what makes code vulnerable? First, we are not superheroes, but also there might be a lot of misunderstandings, either by mostly by programmers, where we cannot know all of C++ with all nifty details at all. Even in the standards committee, there are very few people, and from them that understand a lot. But even from them, you might have to get half a dozen in a room together to have, let's say, covered all of C++, maybe together with the actual standard text as a cross reference. If you're a member of the C++ standardization, you see that there's always discussion ongoing about how to interpret a specific thing, especially just after a standard text has been read or has been finished to be released as the next standard, and implements are starting to jump on to implement the stuff that they haven't done already, and then look for, oh, what does it really mean? One important thing to make your code less vulnerable, regardless of the language that you're using, is have guts. And I don't mean the intestines that are in my background image here, but actually what Kevlin Henney talks about as good unit tests. Having automated test strategy and having a conscious best being test driven design or test before implementation design, that helps a lot with getting your code in better shape, because especially if you're defining the interface of a function or a class type, once you're writing the test cases for that function or class, you end up being a victim of your own design decisions, and that helps a lot to improve your design, and it gives you feedback on what are the things, what things work, and what are unpleasant to work with before you actually release the code, which is the important thing to test as early as possible, in my opinion. But I might be biased because I'm using unit testing for C++ since 1997. So if you look at vulnerable code that we produce as programmers, and even the best ones aren't free from guilt there, uh, what actually might happen is that you have immediately buggy code and that is the code that is kind of either you will very easy find that it's wrong because of the test cases you write. They will figure that out. And also because the compilers might be able to warn you about that if you do something that is so obviously undefined behavior that they are able to actually tell you that it's undefined behavior. Unfortunately, most of the time, it heavily depends if some piece of code has undefined behavior or not, especially on the data. For example, dereferencing a pointer might be perfectly well defined as long as the pointer points to something that is valid and of the correct type. If the pointer is a null pointer, at least you recognize that is something because your program might crash with a segmentation violation on a Unix-like system, or you might have behavior that is doing some wild things because it's undefined, like formatting your hard disk or crashing your computer or whatever, or just doing the wrong thing that is not supposed to happen. And these kind of lurking problematic cases might be caught by test cases, but that requires you to be very good at writing your good unit tests, because it requires you to actually test for error scenarios and might need to have non-local properties to be established through your architecture. And some of those I will cover later in this talk. Now, if you look A common pitfall is also code evolution. There might be a code that is working perfectly well, and then it's either changed due to new requirements or to refactorings or to caring about other bugs, and then it causes other problematic things. Or when you port things, especially from, let's say, older systems to newer systems, like from 16-bit to 32-bit or from 32-bit to 64-bit, that's where a problematic case, especially implementation defined behavior, might, let's say, violate assumptions your code base has, or sometimes even changing a compiler switch or choosing a different compiler can expose those problematic things. Now, what can you do as of today? And I actually might need to change that slide to say, okay, use minus SCD C++20 to 23 and take all the non-standard extensions as errors by choosing pedantic errors so that you don't accidentally write code that's only supported with your compiler and not a different compiler. Again, using different compilers actually might help you to figure out the vulnerable parts of your program, because compilers slightly differ on the amount of static analysis they are able to do during compilation. So might give you different warnings for different for the same piece of same program. Another thing where you can proactively work on is by using the C++ type system, especially strong typing and the library. And the library, I mean, for example, don't write your own loops. Use the standard library algorithms to actually, which cover many of the problems that you might intend to write a loop for. When considering the MISRA-C guidelines that were released last year, the end of last year, we almost got in a rule that told you as an advice, don't write your own handwritten loops except for the range-based for loop. And unfortunately, we got too much pushback from the reviewers that it didn't make it in the final document. But we still plan to have that rule in the next release of the MISRA guidelines. And if I can have a say in that, I will try hard to get there. So please be prepared. Benefit in C++ is what is quite unique to the language is its deterministic object lifetime and its killer feature, the curly brace, that actually cleans up all local stuff. And having destructors being able to do that cleanup work is really an important thing. If you want to learn more about when and how to write destructors or all these special member functions, there have been other talks by me on what classes we design and how. It's a title, and unfortunately, only very few were at my workshop on Wednesday, where I got into deeper thoughts about how to deal with special member functions, which is I skipped this time. Treating all compiler warnings as errors is also something that there's really one annoying in a piece of code you might actually, where you know, okay, it's okay that the compiler warns, but this code is still correct. I can prove that. Then turn it off locally with the corresponding compiler pragmas to be able to actually show that you cared and know, and otherwise you will the code is still checked. That's a good thing. Not turning them off on the command line is helpful, especially when you provide libraries. Your code should actually be warning free. Um, Use static and dynamic analysis tools. For example, Clang Tidy or even commercial static analysis tools help a lot with avoiding vulnerable code. And dynamic analysis, at least for test cases or for testing, use the sanitizers provided by modern compilers. And avoid the bad stuff in your programming. And what is the bad stuff? Well, there are people who actually work on collecting the bad stuff of your programs. The corresponding ISO working group is WG23, which is different from WG21, which cares. 23 is caring about programming language vulnerabilities, and the standard are all ISO 24772. Um, there is a language independent part that tries to cover, let's say, the most common bad things that languages or programs might be vulnerable to. And then there are different subparts that cover specific languages, like the -10 part for C++. And if you look at the handouts, there you can see actually the link to the public version of the draft of the -10 document, where you can actually take a look at the progress of the work. It's updated whenever we update something in the working part. And if you have feedback on that, I'm happy to forward those things to the authors, and which include me, of the vulnerability guidelines. The structure of these things, I just show you that the general part has some kind of description of the vulnerability, the coding guidelines where it might be um, um, drawn from, and then the mechanisms of failure, the language characteristics, like a language without pointers. You might not be able to have a null pointer dereference unless it's pointers in disguise, like in Java. And avoiding vulnerabilities is the important part that tells you actually what to do or what not to do to not fall into the trap of the situation given by the vulnerability. And there's even implications on language design and evolution. And sometimes the languages you can actually see that they paid attention to changing things. An example of the general document says, okay, pointer arithmetic for languages that support pointer arithmetic. Um, you get into problems with pointer arithmetic. And the point is, what are the mitigations? Well, um, you might not use pointer arithmetic, at least not directly. It says about indexing in C++, I would say, use range algorithms, and then you delegate the maybe underlying pointer arithmetic to the iterator mechanics of the or range mechanics of the canned algorithms that hopefully don't have silly bugs in their implementation. If you look at the vulnerabilities, I just give that as a reference. We have 6.2, which talks about the type system vulnerabilities, up to 6.65. And if you count correctly, there are 64 vulnerabilities. And it's interesting that we even managed to get a two-based index there, but that's because of the numbering scheme. And there's a lead in chapter called 6.1 in the general document. Now, that is too much to actually follow, but nevertheless, to give you an overview, there is even a summary that gives you what are the top 5 avoidance mechanisms to actually make your code less vulnerable, regardless of the language that you're using. And the most important thing is actually check your preconditions or your inputs, and check the error returns um, from your functions, and enable all compiler warnings and static analysis that you can do. And if you do indexing, which I think is something that is no longer necessary in C++, uh, perform a range checking. And the last thing, or the sixth thing on the top 5 mechanism, is allocate and release resources on the same level of abstraction, which is trivial through C++ destructors and manager types that allocate in the constructor and release in the destructor, which is had been long time called RAII, or scope-based resource management. So that's kind of trivial to solve with the mechanics of the language. Nevertheless, you have to wrap things that haven't had wrappers yet. And that's again something you can learn in some other talk that you might be able to watch online from me, what classes we design and how. Now, how can we make our code less vulnerable? If we look at vulnerability, for example, 6.7 in the vulnerability document is string termination, which is an issue in C very much, and is an issue, or used to be an issue, in C++ as well. However, if we look if we write code today that looks for this string termination by hand, by handwritten loops, for example, that is something you would never do in contemporary C++. Just use standard string, full stop. There's no guarantee that string view or span, if you use that for character sequences, would guarantee you a null termination. And therefore, standard string is guaranteed to be null terminated and easily to pass the corresponding buffer to a C-style API that requires null termination, which is not true for string view and span. And as long as you cannot prove that it's real performance deficiency in your program that you're not using standard string, I would say not using standard string for string types is something that makes your code vulnerable unnecessarily. And actually, in the safety critical domain or security domain, I would say it's malpractice already. Now, what is the general resilience advice, regardless of individual techniques? And it's something that has been foundation of my teaching for more almost 2 decades. And the most important thing is use value types. Actually, languages and processes are quite good at copying stuff around, and value types just allows you to write in a functional style where you have fewer side effects or almost no side effects, and where passed by value, the called entity function or whatever you're passing a value to has its own copy. So any changes made locally don't have any effect to the outside world, which is a very makes it much easier to argue about the code that is written and to live with it. There is nevertheless something where you might need something pointer like. There might be the need for side effects in your functions for whatever reason. One side effect that's typical is anything that has to do with I/O, and you might have data structures that you create yourself where there is some linkage between elements necessary, or you might have objects that you want to pass a call chain where the objects themselves are non-copyable, which is something you might need to actually establish. That is the need where you have what I call a relation type. And I have more on these types a bit later. And these relation types is something you should make much less use for. For example, in the past, you might have learned using const reference as function argument types so that you save the copying and make sure that it's not an overhead through copying of values. Today's systems are quite fast, and actually passing by const reference, depending on the object size, as long as it's not too big, might actually be slower than just passing by value. So that's something to consider. I would say only use const references today if you can, either in generic code where the objects might be really big, or when you can actually prove that it's faster than pass by value. Also, the type system is something to appreciate. It's actually there to help you to avoid writing bogus code, like interpreting bits in the wrong way. And that's the main reason for having a type system. And the C++ language mechanisms allows you quite very strong typing, where the you can make your own types act in a way that is either indistinguishable or almost indistinguishable from the built-in types, and with the benefit that that as a type author you can actually control what functionality exists for the values of your type, and also how it interacts with other types, especially with respect to implicit or explicit conversions that are allowed, and let's say mixed operations that might be possible, which are one of the big vulnerabilities of the built-in types. A next thing is what is corresponds to the list about the do something about the errors that the function might actually return to you, and having a conscious error handling. Unfortunately, there is no single mechanism that fits all needs, and it's heavily context dependent what mechanism you're actually use in a specific case. The important thing is caring about the errors, or at least consciously saying, I ignore the errors. I show you a little bit about that in a couple of minutes. Now, no legacy loops, I already told you so, and the consequent use and design of manager types for resource management to get the acquire and release in a logical connection instead of having to call completely independent functions like malloc and free or other C-style APIs where you have different functions for the acquisition and release of a resource. Compiler warnings with errors, sanitizers, and encapsulate the bad stuff when it's unavoidable. So again, a lot of guidelines actually have rules in them, like the MISRA-C guidelines, where the authors of the guidelines know that you have to violate them occasionally, but the rules are there that the programmers actually only put that violation when they have deeply thought about alternatives and need that and encourage them to encapsulate the bad stuff. So when I teach and talk about C++, I talk about different kinds of C++ types. And most important, I already used that word value types. Types is value semantics. And with real value semantics, where the copying and everything just works. We have the relationship types or relation types, and those are the things where other languages like Rust, for example, try to make them less vulnerable, but in the end, you end up in situations where you still have vulnerabilities. And most of the vulnerabilities that you need to retain, even in contemporary C++, is the situation of avoiding dangling. And because whenever you access a dangling relationship, what happens? It goes boom, and that because that bang that it makes is very close to dang. I borrowed that term of dangs, I think, from I forgot who I borrowed it from. It might be somewhere in the handout. So I use dangs and relation types because they can go dang. In C++, we also have the ability to have runtime polymorphism, and those I call polymorphic types. And whenever you have used the keyword virtual, you were exposed to that. In modern C++, using virtual is not the only way to get variability. And I would say most of the time, virtual has been overused in the past for things that either not varying at runtime or have no need to vary at all. And too much abstraction and too much virtual is can be problematic. So unless you're really doing an OO style type with arbitrary extensibility, uh, then your architecture might benefit from reducing the need of using virtual. And then we have the manager types, which do all the resource management for us, like string, vector, or you name it. And you can also DIY. What are value types? Scott Myers has a famous quote: "Do as the ins do." The built-in types, behaviors, value types, they are copyable. The copy and the original are completely independent. Values can be assigned unless the variable is or the target type is const, and the copy and all the built-in defaults into the language just work. And if you combine value types within a class, all the default mechanisms of the copy constructor and even the move constructor, move assignment just work. Good. No vulnerability. Relationship types are the ones where vulnerabilities happen. The important thing, there are relationship types that are in disguise, so where you don't have the pointer or reference symbol when you define the type. String views, span, other views are relationship types, and you might even build your own. Sometimes people have things like, oh, I have this row number from a database, and if the database changes underneath, you will end up with having a relationship to something that is no longer there or is a different value now. And that is something to take care about. And that requires superhero programmers to keep track of the validity of any relation that you're setting up. One side mark: managing smart pointers like unique pointer or shared pointer are no relation types. They are managers. And unique pointer is a unique manager, and there are other manager types like that manage the resource. So even if something has underscore PTR in their name, they're not necessarily relationship types. For polymorphic types, if you insist on doing so, there are a few things I'd like to say about. Um, Only use them when you have the need for runtime variability and unlimited extendability. If you have a few cases, even a standard variant might be a better way to go around with, because you might actually be able to copy things more easily than you get with virtual functions. If you have virtual member functions, make your destructor virtual as well and default its implementation. It is very rare to have an abstract base class where that is also a manager class where you would implement the destructor, and prevent copying and the, let's say, smallest amount of code to prevent copying in the abstract base class that you are in the base class that you're defining is by making the move assignment operator define it as equals delete. And that's the only case where you would actually define a move operation as deleted. All other cases are ridiculous. But here, this actually prevents the copyability and movability of the base class, so you don't get slicing and you don't get accidental copies that you don't want to get. Manager types, deport, are those that actually implement the destructor that does something. If you have class types that define the destructor with an empty body, just delete the destructor. It's completely useless and just cluttering your code, and you don't want that. When creating your own manager types and not just combining existing managers, make sure that you try to manage only a single resource. I tried myself to getting managers done for more than one resource. Don't do that. And there are different flavors depending on copyability. A non-copyable manager is a so-called scope manager, which you can observe in the standard library, for example, with scope guard, which more or less protects the scope with the mutex or with the mutual exclusion mechanism. And then we have unique managers like unique pointer that allow transfer of ownership. And we have general managers like vector or string that allow copying. And the only differences are how to create them, how much effort you have to spend into actually copying or move implementations. And for DIY cases, these scope managers might be just sufficient. Now, if you look back at our top mitigations is input validation and a return check. And I'm just going quickly. If we look at the concept of contracts, which aren't in the language still, but might come in SEC 26 after we pulled them for T++ 20. But nevertheless, regardless if we have contracts in the language or not, there will always be preconditions your function assumed to have if they are specified or spelled out or not. And sometimes it's something a function can check. That's where the built-in contracts in the language help. But sometimes it's something a function cannot check, and you as a programmer are responsible to actually create the arguments to a function call or a template in a specific way that it's not violating the preconditions. There might be post conditions what a function actually guarantees. Most of the time, if there are all preconditions are satisfied, post conditions satisfaction is only the responsibility of the called function. However, if the function depends on some external state like the operating system or so, there might actually be situations where a post condition cannot be guaranteed. Having a problem in your program is called a fault, and this is either a precondition violated by the caller or that a post condition cannot or wasn't satisfied. Now, when we can actually detect the fault at runtime, we create a so-called error, and that is when we can actually deal with the situation in a fault-tolerant way. And there are easily 5 different ways to deal with errors, and what that means is your function contract is violated, so your function can do something about it. The one approach is that is the fastest and sometimes deliberately used by the standard library. Ignore any kind of faults, especially when there are precondition errors, and just have undefined behavior. Using the front member function of an empty vector is undefined behavior because front wouldn't check that the vector is empty. And what undefined behavior means depends on the implementation. If you have a safe vector implementation, it might throw an exception. If you otherwise, it might just give you a bogus reference back, and that can be interesting later on. There are more mechanisms to note an error. The fourth one is actually throw an exception. There are others like error status as a side effect. Like for those of you who have seen Erno in the past, then the um, you might have been hit by situations where you had to check Erno, and when you actually checked Erno, it might already have changed because of another system call happening. That's kind of the problematic side state of having a side effect. Now, the best functions are those that cannot fail, so they operate on all of their valid of their input range and always succeed. They are not uncommon, but sometimes you might need to have special parameter types that do the checking of the validation already when constructing the corresponding value, so that a function doesn't need to check again. And that is a trick of using strong types accordingly. Now, these so-called wide contract functions that cannot fail, they might be marked with no except, but it's not necessary. But it depends on the situation if it's a benefit to mark that no except or not. The only functions that you must mark with no except are the move operations that you define for a class type, because defining those without being able to guarantee that they won't throw exceptions is kind of ridiculous. Then all destructors are implicitly no except, so they will actually get that no except marking implicitly, so you wouldn't throw any exception from a destructor unless you want your program to terminate when another destructor, when another exception is already in flight. I'm guilty of defining once a type that had a throwing destructor, and I refrained from pursuing that track beyond the standard library fundamentals technical specification, where you have a scope success class that actually throws. Now, if we have narrow contract functions, those that have preconditions and can check those at runtime, you must not mark them with no except. That's one of the design rules of the standard library. And as you want to terminate your programs. And what that means, if someone triggers that actually precondition violation, that means the caller of the function, the programmer that calls that function, actually made the mistake. So the failure mode is actually the programmer error. And somehow you better get rid of those failures before you release a system. Yeah, if you have functional
Questions, if you want to take them.
Okay. There's a saying about I can see something by David that says, as a safety car talk, in case of safety requirements of software using new C++ features, it's recommended by guidelines. Sometimes that's just breaches to acquire. Does it matter for the software safety analysis? But I'm not sure if David has anything to actually ask. He is more or less saying what I didn't say in my talk because of the timing. And then there's function which handle out of contract cases, don't technically have out of contract cases. They have wide contracts. Yeah, that's a philosophical question. I dare not to go too deeply. If they care, let's say, if a function throws an exception in case of a precondition violation, some people say it's a wide contract function because there is a defined behavior, meaning it throws an exception. That's heavily depends on what does it mean to getting that exception. If that exception is never handled, it means the program terminates, and so it's still a programmer error, and I wouldn't call them white contract functions. But that's kind of a discussion philosophy in the sender library implementers have, and I dare not to put, let's say, I sometimes put on two different set of glasses depending if I consider those white contract or narrow contract. If it terminates with an exception, I would say a contract was violated. But most of the time, but sometimes I can understand the argument that okay, if I have defined that I throw an exception in that case, as a function author, I have defined the full. I have defined the full range of possible inputs, and the exception is part of my API that you have to care about. But again, if I expect a contract violation by my caller, I might do something else. Now, if we look for functions with external dependencies, there the failure mode is kind of built into the function. And as a general, let's say, strategy, I wouldn't use exceptions for signaling problems with external resources. Java did so, and it was kind of very unpleasant to work with. I would make the function return uh, correspondingly error situations, and there are different means on how to do so. And Herb Sutter has a full talk on what to do with error taxonomy, where he more or less creates that table. And please be free to look at that. And there's another thing now on you need to be careful to use string views where an ultimate string is expected. Okay, I already said so, though that's just preaching to what I already tried to say. Now, if we're looking at error handling strategy, the important thing is to have a conscious error handling strategy, and it might be heterogeneous in your system. So I wouldn't use exceptions for saying a file is not found, but it heavily depends on the context of your system and your calls if that is really the best way to do so. But the important thing, once you have an error strategy for a given function, you can actually write test cases for it and also test the error situations. And if you have external dependencies that are hard to get right, then you might actually need to have a dependency injection, like an extra parameter that gives you a means to actually check the logic without having to change your, let's say, delete a file on your system. And that is something where you might use templates for injecting errors into test case code. Now, back to another topic, which I try to rush through. The important thing is dealing with relationships is hard, especially for humans, but and between humans, but also for programmers within program parts. And there are, let's say, things that are types in C++ that uses star or a reference symbol and ampersand to denote, okay, there is some relationship going on. And I already said there are all these hiding things that hide a relationship. Now, if you look at the vulnerability lists, there are more than a dozen vulnerabilities that care about pointers and pointer-like things, where a dangling is important part. It's even a dangling between references to a heap and reference to stack frames. When we looked at the dangling reference to stack frames, I learned about stuff that people attempt to do, which I would never have the brains to come up with, and which are quite undefined in C++, but people confess to me they either have done it themselves or have seen it in code bases that they were reviewing. And it's that's when you just hold the hand on your head to get there. Now, I like to use a German word, which I call Fernwirkung. Having these relation type always using them in an expression where you have some computation allows you to have what I call Fernwirkung. It's kind of a remote effect that you get there. And that is the important thing. It enables us to have things like abstraction, and it enables us to have things that are non copyable and still make them useful. And the most useful part for relationship types are actually as parameter types for normal functions, because then the language mechanisms usually guarantee that there is no dangling. If you have them as member variable types or as return types, it's very easy to end up in a situation where they dangle. Now, the Fernwirkung is kind of what I define as excess to modify something that is not part of the current expression. And again, all these relationship types allow to do that. And there's a lot of technicalities like, okay, this is where you need to put on your superhero cape to keep track of the lifetime and validity of that relationship. And if the target of the relationship is destroyed before you really have forgotten all of the relationships, you end up in dangling. You might have situations with iterators where there is even invalidation happening through changes of the underlying container, which is far more tricky to avoid than other things. I think there have been talks about ranges and views where people were trying to show you that views are broken because the caching that works when the underlying structure is not changed breaks down completely when it's changed while you're using the view. But that's again like iterator invalidation that happens, then that breaks things. Um, if you have a member variable that's a relation of a relationship type, then you end up being contagious. The class that you define is also a relation type, unless it becomes a manager and actually manages a relationship. For example, unique pointer as a pointer member for obvious reasons, referring to the managed memory, but that is not doesn't make it a pointer because unique pointer will actually manage the underlying memory and not give you unless misused, not give you back the raw pointer to a dangling memory segment. Now, what is safe to use? Well, there are a lot of things, and the most important thing about plain pointers, they have too many issues to deal with, and we are running out of time. Therefore, I'm rushing to the comic version. So, one thing that's good, I already told you, if you have a variable in a given scope, then you pass it down by reference to a called function, and that function returns the original variable. That's all good. Nothing bad can happen uh, normally, unless the function you're calling is a threat or a coroutine, which can suffer from dangling when they have reference parameters. Now, if you have a global, that's also something that cannot dangle, but it's dangerous because it's kind of a super glue between your code and the global variables. And if you have multiple uses of the same global variable, that's quite untestable in isolation and also have interesting effects because of side effects that have remote effects. Now, one thing that you can do, get rid of global dependency, but still have the global lifetime guarantees is by passing them from the high level scope down the call chain by reference. And that helps. For example, I teach C to my students to not use standard C out or standard C in their functions, but always pass an IO stream or iStream or OStream parameter instead by reference so that they can test their functions that try to make IO and only use C in and C out objects in the main function as arguments or very high up the call chain. Never return relations. Fortunately, most compilers warn you about that, unless you're returning something like a string view to a temporary, which is not easily caught by the compilers today. Um, Again, returning relations to parameters might work, especially when you implement things like a container, where you want to refer to an element and search in the container and return an iterator or reference to the element. But that again can easily fail, and that requires some superhero capabilities to keep it working and not accidentally dangle. Threads are very easy to get data races if you pass something by a relationship type, and if that's necessary, you need same with globals from threads. So what you actually need is atomics and mutexes either by reference or from a global scope so that you actually have the ability to share without having data races. In C++, the typical issue of references to the heap, like double release, this excess of memory, is actually solved with a shared point, a unique pointer. Sorry. Memory corruption because of out of bound accepts is actually solved by using containers and iterators. And the only thing is the dangling, the excess of memory after release or excess of memory after invalidation. That is something where you still have to wear your superhero cape and goggles to make it work. So I already said use manager types, and you're all set with the allocation and release. And don't have new and delete in your code bases, and don't call destructors directly or destroy it unless it's tightly encapsulated when you implement your own containers, and use address sanitizer, at least for test code, to find the obvious bugs. And if you still have code bases that have things like new and delete in them, refactor away. Do so. You heard it. It's unprofessional as of today, since C++11, I would say almost, or 14 in the case of unique pointer. Now, there are still dangling reference to stack that can have similar problematic things, like something that looks kind of not very problematic, the max function of the standard library. It takes parameters by const reference because of reasons, maybe traditional classic things, and that 20 actually gets materialized as a temporary, the const reference bound to it, and Max might actually return the const reference, and you can bind a reference from its return, which looks almost good until you access it, and it was referring the temporary that was through the 20 manifestation, and that causes immediate dangling. And this can be, and this is even data dependent. And that's an example I might have been hit by. The main thing to learn: don't use lifetime extension of temporaries through const references or R value references in your code base. People pretending to do so to actually speed up their code. It's kind of dangling and lurking, and don't do it. Copying an integer might even be cheaper than copying than keeping track of the reference that dangles. There are more peculiarities. You get lifetime extension if you access a sub-object of a temporary, but not if you access the sub-object through a member function, and that you have lifetime extension at all, and only that particular part of it was kind of a compromise, and you can read about that in Design and Evolution of C++, and that is something where pragmatics caused something among the many possible trade-offs that could have been chosen, and we cannot change that in language definition at all. The only place where we changed it was the range for C++23, if you want to look for that. And I skipped more of the examples. You can play around them with the Godbolt link. And this is something you see if you have a function that returns a vector of strings and want to iterate over the first string of that vector, assuming it's never empty, the vector, then this causes immediate dangling because the underlying string is destroyed at the end of when this expression was evaluated, and is not lifetime extended through the range for up to C++20. In C++23, that is fixed because the lifetime extension for range 4 has special cases now for not making this pitfall happening. One thing to avoid is, for example, if you look at a canonical assignment operator that returns the actual L value reference to the object that is assigned to. If you make your own assignment operators with the ref qualified, you avoid returning a reference to a temporary, which is also something that can happen, and play around with the Godbolt link at home. And I'm running out of time, and I could talk more about the built-in numeric type problems. One thing, ever knows the type and result of the expression from the top of their head, that's actually Oh, there was a question on my example on page 51. I think I need to tell you something. Yeah, function G returns by value, but here you actually, at the M, you see you access the const reference to a dangling value. So the dangling actually happens here, not on the return side of the return statement itself is dangling. If that answers Andre's comment. So that is actually the dangling access happens when because the temporary dies at the at this semicolon here, and that is when so we get immediate dangling of the reference M, and therefore it is a bug. Built-in numeric types. Maybe I should submit another talk going more deeply into that. And there are people on Twitter that have very bad things about the type system, and there are a lot of things going on. And um, just to wrap up my talk is, in general, use value types where possible, pass by value, return by value. You cannot avoid them completely, but reduce the need for having pointer-like things or relationship types and only use them as parameter types for regular functions. Avoid using the built-in types directly. Most of the time, your domain might ask for not an int, but a counter of whatever rubber ducks. If you are rubber duck management software, then you might want to have a type for accounting rubber ducks instead of using int. Um, Use conscious error handling. So maybe you cannot have negative rubber ducks or no legacy loops, because most of the loops have been written for you already in the standard library algorithms. And there are many cases where people refrain from using the standard library or the algorithms, and they are wrong in doing so. And a friend of mine even did a study on how range-defined or algorithm-defined code actually was faster than handwritten loops, because the compiler can do more optimization, or the algorithm implementers are a bit more clever in algorithm design than you have been in your university studies or wherever you learned about that. Warnings as errors, manager types, encapsulate the bad stuff if you cannot avoid it completely, and don't spread it around your system, like insisting on passing and returning pointers from functions. That is something that makes your code very unpleasant to use and very easy to use wrongly. And I think I'm supposed to show up in Town right in a minute or two. If there's anything. Oh, there's even more questions about why doesn't it get lifetime extension? Oh, there's one question where is there a good reason why range for lifetime extension wasn't put into as a defect report in C++20 and previous? I don't know. And maybe it is, and I haven't been aware of. So then doesn't it get lifetime extension? That's still about this example, I suppose. And this n doesn't get lifetime extension because max is a function, and lifetime extension never works across function. If the max function would return by value, then the returned value would have been lifetime extension. But the max function is defined to return by const reference. And that means the const reference to the temporary that was contains the value of 20 in the case that's a result of max, then that reference return is immediately dangling because the temporary is destroyed at the end of the full expression, which is marked here by the semicolon. And that means there is no lifetime extension. This code is immediately dangling. And I'm not sure if I have, no, yeah, you can try with address sanitizer and .bolt if you can get that. If not, you can send me the link and we'll see if I can make it work for you. Yeah, the temporary lives inside the standard max and not there. That's the correct conclusion. And let's go back to the end. So feel free to ask me things. I'm happy to answer questions on my social media or even via email if it's not public. And again, remember, I'm available as a trainer, coach, consultant. So if you need a voice within your organization helping you to get rid of bad code, I might be one to help you with that. And see you over in Gather Town or wherever you meet me. Next time to see me in person would be the ACCU conference in Bristol, if things go well, or the using standard C++ in Madrid the week after that in April, or whenever you hire me as a trainer. And I conclude now and stop this. I'm not sure if I should just stop sharing, and I hope my uh, colleagues will help me with that.